This massive collection of tubes on the wall here is really just a large-scale recreation of this. And what is this, you might ask? Well, this is a minimal ICU system as outlined by Motorola in the MC14500 handbook. What is the MC14500, you might ask? Well, it's a 1-bit industrial control unit, a microprocessor essentially, and it's this little IC right here. And I have essentially recreated this IC with all of this. That's 190 vacuum tubes. Now, I've made a couple of modifications. This IC only has a logic unit, whereas this now has a proper full-on arithmetic logic unit with a carry register, so we can actually do addition and subtraction on that. But other than that, they're pretty close to the same. The rest of this, though, I'm trying to build in just this tiny amount of space, which seems ludicrous and impossible, but a lot of the complexity on here is right up here in the program control, because we have a stored program on a ROM and we have an 8-bit counter, and I'm eliminating all of that by building something that's going to sit right here to read paper tape. But getting it to read paper tape is a pretty big challenge. I'm not just going to buy some generic paper tape reader that was built in the 70s. That doesn't really fit with the aesthetic and the theme that I'm going with here, which is trying to build as much myself as possible. So we're going to try and build a paper tape reader from scratch, and that is tough. So I've got some ideas, I've got a bit of a plan. So let's sit down, figure out exactly what it is we're going to start machining up today, and then let's fire up the mill and start making little bitty chips of aluminum. Just in case, if there is somebody out there that hasn't seen the previous episode or any of the previous episodes in this series, welcome to the UE1. This is a very strange project, and it's been going on for a very long time. So just in case, I want to do a quick little recap of what we've built, why it's very weird, and where we're headed from here. Like, what are we going to build today? So if you have watched all of the previous episodes, I don't know, I'm probably going to cover a lot of stuff that you already know, but I do want to say that I don't write scripts for any of my videos.
You don't say!
So if you do hang around and you listen to this little recap that we're doing, who knows, you might hear something that surprises you. Heck, I might hear something that surprises me coming out of my mouth. I'm over here just winging it, hoping for the best. So anyways, what have we built? Well, we started with what I call the UE14500. This is a recreation of the MC14500 1-bit industrial control unit. And I have a little block diagram for it here. You can see it has a ALU, a carry register, a result register, has some other supporting stuff that goes with it. So we've got that built, but we need to do something with it, because a CPU in and of itself is quite boring. We need random access memory, we need read-only memory, we need input, and we need output. And again, Motorola had a minimal ICU system. This was that blinking lights board that I had at the beginning. But this essentially has an 8-bit program counter that feeds an 8-bit memory address into a ROM. That ROM gives an 8-bit value out. 4 bits are used as an instruction for the MC14500, 3 bits are used as a memory address, and 1 bit is a chip select. We are essentially building exactly this, only with the UE14500 in the center here instead of the Motorola chip, meaning we can do addition and subtraction. That's really the only difference. Well, and it's made out of vacuum tubes. That's a pretty big difference. So you can see we have our 1-bit data bus over on the right. We've got 8 bits of random access memory, and these are accessed when the 4-bit memory address is 0000 to 0111. As soon as we get to memory address of 1000 and up, we start doing funky things, and we bring in the write pin coming out of the UE1 CPU over here. But we still need to get these 8 bits up here at the top, the 4-bit instruction and the 4-bit memory address, into the system. Now, the conventional way to do this, I think, would be to have an actual program counter that is counting up and reading instructions out of memory. And you can load those instructions into your random access memory in a variety of ways. You can do it with paper tape, you can do it with punch cards. There's a lot of ways to get instructions into memory, but we don't have memory like that. We don't have core memory, we don't have a rotating drum. There's no real place to put these instructions. So instead what we're going to do is we're going to read instructions directly off of the paper tape. Now I've got a paper tape here, and if we spread it out here, you can see there are 8 bits with a 9th row that has tiny little holes. So that 9th row is actually going to be our system clock, which means that it will run at whatever speed the tape is going through. And so we need a pretty reliable and clean way to read the data off of the tape so that we aren't getting bad instructions or we're missing clock pulses or anything like that. So in order to do that, we're going to read this tape optically. Now, in the previous episode, I talked about a whole bunch of different ways that you can try to read tape optically, but ultimately I ended up finding some very small photodiodes that are the exact diameter of the holes in paper tape. So that's going to work absolutely perfectly. And before you go running into the comments screaming, "That's not period correct for vacuum tube computers," I present to you Exhibit A, which is the Bendix G15, which does exactly that in 1956. Now, Bendix would read the paper tape and put it onto the rotating drum memory and then execute it off the rotating drum memory. We're skipping all of that. We're just executing it directly from paper tape. So what we need to build today is a way to actually read that paper tape. In the previous episode, we figured out the electrical side of it, just the photodiode with a 100k ohm resistor feeding into a simple 6A6 inverter here that's providing the output. Seemed to work really perfectly. This is exactly what we're going to do for the electrical side of it. It's the mechanical side of it that's quite difficult. I mean, you can see that the paper tape here is very small. As a matter of fact, if we look at this page out of the IBM manual, we can see the size of the holes are actually 0.072 inches and they're 0.1 inch separated from each other. And actually the even smaller tractor feed hole down the center that we're going to use as a clock is only 0.046 inches in diameter. Now in the previous episode, I had mentioned that I was going to try and do this with the CNC aspect of the mill, and you guys left a ton of excellent comments about different 3D modeling programs to use for that. But I started thinking about it more, and I really want to try and do this by hand. So instead, what I've done is I've drawn out exactly what it is that I'm going to build here, just with, you know, like rectangles and circles and little hashed lines to show how far things are away from each other. And I'm going to try and machine each of these individual pieces by hand, thread them by hand, and then clamp it all together so that it works perfectly. I have no idea if I'm going to be capable of doing this, and if I'm not, well, we've got all the measurements here. We can punch these into a 3D modeling program and then let CNC take over from there. But I really think that using the DRO on that mill, I can get this by hand, and I think it'll be pretty awesome. So instead of sitting here trying to explain to you exactly how this design makes sense in my brain, I think the best bet is to build it first, then show you all of the individual pieces, and then assemble it and show you how it fully works. So that was a lot of talking, but now it's time to get to action. Let's spin up the mill and start doing stuff. We already have a ton of scrap metal hanging about, and the last thing I want to do is go buy more. So instead, we're going to build this thing out of scraps that I have, starting with this leftover piece of aluminum bar stock. I need to extract a tiny little piece out of the center of this thing, so I'll just make a quick mark and then carry it over to the bandsaw. This is just a first rough cut, so I'm not dealing with the whole piece, which means I don't have to be super accurate yet. I'll just let the bandsaw do its work and slice me off a small chunk to work with. Unfortunately, our bandsaw isn't exactly square, and I haven't spun up the lathe in a while, so let's give it a whirl. I'll mount the piece in the jaws, then pop open the pulley cover and loosen the tension. Aluminum is a pretty soft material, so I want this thing spinning pretty quick. I'll move the drive belt over a pulley, then pop open the top cover. Under here is another pulley set and reduction belt, so I'll just adjust them too. Then let's get this piece spun up and start slicing metal. I want to make the face we just cut on the bandsaw perfectly flat. That way I have a known good flat surface to start building from. And you can see just how not square our bandsaw is. The first cut on the lathe only got one small portion of the piece, so we'll just keep plugging away at it, taking bigger and bigger chunks. There are all sorts of guides out there about the perfect spindle speed and feed rate and cutter angle and depth of cut and all sorts of stuff. But I'm here to have fun, so I just kind of experimented with it until it felt like I was getting good clean cuts. And yeah, look at that. That is a perfectly flat surface. After doing the other side, I now have a round piece with two perfectly flat ends. That's still way too big. This measures in at 53 millimeters, and I need it to ultimately be 46 millimeters, and a rectangle instead of a cylinder. So off to the mill we go. It took a bit to wake the mill up from its months-long slumber. I don't use it at all during the summer, as it's just way too hot in the garage, but it's been cooling off lately, and it's time to get the big girl going again. Like the lathe, I kind of experimented with spindle speed and feed rates, but it's been a long time since I've done any proper machining. Still, I need just a 10mm by 10mm by 46mm rectangle to come out of the center of this chunk of aluminum, so I have a lot of room to play with here. I want to get one side down to a perfectly flat surface, as well as take away a lot of material, working towards that 10mm size. And yeah, that's looking pretty good. Time to flip it over and do the same on the opposite side. Slowly but surely, I'm wrangling this thing from a much too large piece of round stock down to a nice little rectangle. I've got the piece down to pretty skinny, so it's time to flip it on its edge and start working my way down from there. But one thing I'm relearning is that mounting the piece in the vise is the hardest part by a mile. It's so easy to get it slightly wrong and end up with skewed lines. And you can see just that here. The top here is at a different angle than the bottom, and there shouldn't even be any angles. The thing is supposed to be square. So back into the vise it goes, and I'm starting to refine my mounting strategy. I use flats, I think that's what they're called, or pieces that are certified to be, well, flat, to align the piece. Then I clamp it down hard in the vise. Fortunately, I have a lot of material left to work with, so I'm confident I can get this thing back to square. Make no mistake, machining things is hard, especially when you're making kind of dumb mistakes. One time I didn't get the bit in as tight as I should have, and so the bit was moving slightly, and so that made my piece have a slight angle to it when it should have been totally flat. Another time the bit got gummed up and it wasn't cutting correct, and that started to chatter along the top, and that was ruining cuts. I'm getting there. I'm slowly getting there. And we started off with that big fat round piece, and we're down to kind of this little block, and we need to go even further. I need this to be 10mm by 10mm. So it's a quite small block, so I gotta keep slicing away at it. But we're finally at a point where it's square. The distance here and here is the same, and the distance here and here is the same. So I'm starting to get the hang of it, and I'm starting to get this to the shape that I want it to be at. So we're just gonna keep plugging away at it until this is the shape it needs to be. Then we can cut the grooves for the photodiodes to sit in. There's still a lot of material left to take off of there, so it's back into the vise it goes, and we'll just keep chipping away at it. I'm getting better at learning how much of a cut to take to prevent the bit from getting loaded up with aluminum. And for the rest of this, things start going much smoother. After getting the two 10mm dimensions taken care of, I need to shorten the piece down to 46mm exactly. I'll slowly work down the side to make it flat and square, then flip and make the other side flat, then remove it and measure and figure out how much material to remove, then slap it back in the vise, zero everything out, and take off the required amount. If it sounds super tedious, don't worry, it absolutely is. All right, Stella got her groove back. Check this out. I need it to be exactly 10 by 10 by 46, and if I measure it that way, there it is, 46.03. Absolutely nailed it in that dimension. I am a little fat in these two dimensions. That's 10.25 and 10.27. But they're so close to each other and so accurate that I think I'm just gonna leave it like that. If I need them to be smaller, I might, I don't know, sand them or something, but that is awesome. I am super happy with that. Now we need to cut grooves in it for the photodiodes to sit in. Now comes the hard part. I need to make some V-grooves for the photodiodes to sit in, and we talked a lot about this over on the Discord, and there are many ways to tackle it. I could mount the piece at a 45-degree angle and then use a flat end mill to cut 90-degree grooves. I could rotate the mill head, then retram it when I'm done, but ultimately I decided to just use some V-bits. V-bits have a lot of drawbacks, and this is stepping out of the proper use case for these bits in particular, but I ran some tests on some scrap aluminum, and they cut well enough to get the job done, I think. Also, I have a bunch of these 60-degree V-bits hanging around because I use them to cut my PCBs. So if I destroy 1 or 2 bits in the process, it's no big loss. I'll slowly step the mill across the x-axis, then cut my V-groove in increments, plunging about 0.5 millimeters each pass. Ultimately, I cut to a depth of 2 millimeters, which in testing seemed like a good depth. Finally, I need to drill some holes in this piece. I punched pilot holes on the mill, then I moved over to the drill press for the final hole. And my autofocus is absolutely going to have a panic attack right here, so you'll just have to use your imagination. These holes need to be threaded, so everything that gets clamped into place clamps into this piece. And in order to do that, I just pull out a tap and slowly cut the threads by hand. This is also super tedious because the tap gets loaded up with cut aluminum very quickly. There's a lot of 3/4 of a turn in, half a turn out, over and over and over. Despite being slow going though, we got there in the end. And this is definitely the most exciting piece. It was also the most difficult to make. The little V cuts there, the V bit wasn't perfect. I kind of knew that it might mar up the aluminum a bit, but it doesn't matter. The photodiodes are just gonna sit in those grooves and then be clamped down. So there's another piece that's gonna go on top of this to clamp it, and then there's a piece that makes a mask, and there's a whole bunch of more pieces that I gotta make, but this was the piece that I have been losing sleep over for like 2 weeks now. So I am so glad that that turned out. I think I absolutely nailed it. We'll see once I get the other pieces and start clamping things together, but man, that is awesome. After 2 solid days of turning large pieces of aluminum into small pieces of aluminum, I have 4 parts here, 4 tiny little aluminum parts. These all kind of sandwiched together to hopefully make a paper tape reader. So let's put them together. This is getting pretty exciting. These are our 4 parts, and they're so shiny that they're going to wreak havoc on the brightness of the camera, so sorry if it's going a little bonkers. We'll start with this first part that we made here. It's just a simple little block with 9 grooves in it, and these little photodiodes here are going to sit right in those grooves, and there will be 9 of them all along the way here. Now, to hold those photodiodes in place, we built a clamp here, and the clamp has a little groove cut out of it in the center, and I'll put a piece of foam or something on that, and it sits right on top of this piece, and the foam will push the diodes in place, creating a little sandwich of photodiodes there. Now I'm going to have all these photodiodes sticking out the front here, and I need them to actually line up and read a paper tape. So we've got this piece right here, and this piece is a little longer, you'll notice, but it has 2 holes in the exact same place, and then we've got 9 holes right along here. This is going to be our kind of a light mask or something. So all of the photodiodes are going to push up against these holes on the back side, and this piece is going to sit right over top of that sandwich just like that. And then these 2 holes on the right are actually going to be mounting holes to mount the entire thing to the board, but they also hold the guide here. So you can see the guide has a little groove cut out of it here that the paper tape will slide through, and then it has a slot here for light to shine through, and that's going to sit right on top like that. The whole thing sandwiches together, tape slides through, right through here, light shines through, hits the photodiodes, and we have a paper tape reader, I hope. All right, let's go ahead and take a shot at assembling this thing. I'm gonna fast forward through this because I am 100% positive it's gonna be very, very fiddly, especially with the foam that I put on the clamp, but it's necessary so that way we are positive that it's clamping in nice and tight and holding everything in place. So I'm just gonna get cracking on it, and you guys can watch the fast forwarded version here. And here we go, finished product with 9 photodiode leads sticking out the back. Now there is a couple of problems. I don't know which of these leads is anode and cathode, so the whole thing is going to have to come apart again so I can mark them. And as I was cinching everything down right here, I did hear some disheartening noises. I'm afraid that maybe my mask alignment with the sawtooth block here on the back might be slightly off, and that might be putting a little bit of stress on the fronts of the photodiodes as they push into the mask and then everything gets cinched down. But if it's off by like 0.1 millimeter or something. It's very, very minor. So hopefully I didn't crack any photodiodes, but I don't think I did. The slot for the paper tape here I think is going to work perfectly. If I take a little paper tape here and run it right along through there, you can see everything seems to be lining up pretty good. I got a little bit of play, but it's about 1/4 of a hole width, and I don't think that's going to cause any read issues as long as we pull the tape straight. If we pull the tape at an angle, the whole thing binds, but I think that's probably true of any paper tape reader, honestly. And, well, the other thing that I'm slightly worried about is that I think I need to go through and I need to bevel these edges right here that the tape slides along. Otherwise, I think the tape's going to catch and it's going to tear it right there. So I got to take the whole thing apart and I got to go back across these sections, maybe with a file or something, and just bevel those so that it's a nice smooth ramp into the guide and a smooth ramp out of the guide. Other than that, though, man, I could not be happier with how that turned out. That is awesome. It's definitely been a while since I did any proper machining on the mill, and I'm so glad that I decided to try and tackle this project by hand, because machining things is a skill like any other, and if you don't use it, you can lose it. Because it's been so long, it took me a while to get my sea legs back, but once I got about halfway through the project, things really started to come together and go a lot smoother, and I think the result speaks for itself. This was such a rewarding project to get on there and do this by hand. Oh man. But that's not to denigrate the use of CNC. I actually kind of cheated a little bit building this as well because I didn't do it entirely by hand. I used the DRO and I used the buttons to move the table back and forth and the Z-axis up and down, so that way I could get really, really precise movement without having to sit there and try to get my steady hands to move the wheels to the exact spot that I wanted. So it was, I don't know, it was like building it by hand with a little bit of electrical assistance. But, you know, I think the results speak for themselves. This came out absolutely perfectly. It's exactly how I envisioned it in my mind, only maybe not quite as flawless. There's a little slight errors here and there that move things and shift things around, but it's all close enough that I think it's going to work absolutely perfectly. Now, you guys did make a lot of suggestions in the previous episode about good 3D modeling applications to use. There were a ton in there, but I should have specified a couple of my personal requirements here. I really don't like the idea of my save files being tied up in the cloud, essentially saved on somebody else's computer. I really wanted a program that I could download and keep locally on my hard drive and save files that were local on my hard drive. So ultimately, I think I'm going to go with FreeCAD. I think that's what it was. OpenCAD? FreeCAD, I'm pretty sure. My brother uses it for a lot of the really cool stuff that he does, so I can lean on his knowledge and expertise to help me get up to speed on using it. And moving forward in the future, if I do need to do any machining projects, I think I'll probably model them in FreeCAD and either machine them or 3D print them with the 3D printer that I got from NewGP. Thank you so much for that. And we're going to get that set up pretty soon, so I should be able to do both subtractive manufacturing and additive manufacturing, which means that there's pretty much nothing that I can't build in this shop, and that's pretty exciting. But what is next on this project? Well, I got to build a mount to mount this to the backing board over there, and I got to figure out some way to pull the paper tape through, which means I have to come up with some solution for an electric motor for this thing, and I have pretty limited voltages. I only got plus 24 volts and minus 12 volts, so whatever solution we come up with has to use one of those two voltages. So I don't have a good solution for that one. If you've got suggestions of period correct motors or almost period correct motors that fit within those voltage requirements, leave a comment in the below, and I will take all of those because I'm pretty much lost on trying to figure that one out. Now that we have this done, it's time to lose sleep over the next part of the project. So I want to thank you guys so much for watching, and I hope to see you in the next episode.